Good morning, students. Today we will be continuing with our fourth chapter, that is Refraction of Light. We already had an introduction regarding what is refraction, how refraction takes place, why refraction happens, and you also learned about laws of refraction and what is refractive index. So in the second law of refraction, it was mentioned that angle of incidence and angle of refraction, if you take the ratio of their signs, then what you get is a constant. So in the second law, it said that sine of angle of incidence to sine of angle of refraction will be a constant for a given pair of media. So given pair of media means let this be a surface separating two mediums, let it be air and water. So below this line let it be water and above the line let it be air. A light ray which falls on the surface obliquely, when it tries to pass into the second transparent medium, it will bend. Actual path of light ray should have been in this direction, but it will bend, and to calculate it we draw a normal, and the angle between the incident ray and the normal is called angle of incidence. The angle between the refracted ray and the normal is called angle of refraction. And if you divide sine of incidence, sine of angle of incidence to sine of angle of refraction, we will get a constant for this pair of medium. This pair of medium means air and water. If you increase the angle of incidence or if you decrease the angle of incidence, correspondingly angle of refraction will also increase and decrease, and this value for this pair will remain a constant. And it will be a pure number, and there are no units because we are dividing similar quantities. So there will not be any units. And we write it as refractive index. It is represented by letter N, or it is represented by the Greek letter mu. And we write it as refractive index of water because light ray is traveling through air and entering into water. So this is the refractive index of water with respect to air. Refractive index of water with respect to air. And we can have its value. And the refractive index of water with respect to air has been calculated to be 1.33. We will come back to that later. But now, the next thing you have to know is absolute refractive index. What is absolute refractive index? When a light ray is traveling in vacuum, it passes into another medium and it undergoes refraction, then the ratio of sine of angle of incidence to sine of angle of refraction is called its absolute refractive index. For example, if light ray traveling through vacuum is entering into water, then it will bend at the surface separating the two medium. Then we have to find the angle of incidence and angle of refraction. If you take that refractive index there, that is sin I by sin r, then that refractive index is called absolute refractive index. For calculating absolute refractive index, the light ray should be, the incident ray should be traveling in vacuum. So absolute refractive index of some of the materials are given here. Diamond has one of the largest values for absolute refractive index, which is 2.42, and we have glass, the crown glass, which has an absolute refractive index of 1.52. Then water, the absolute refractive index of water is 1.33. So the value of absolute refractive index of diamond is very high compared to that of glass and water. It means that diamond is an optically denser medium and glass is not as dense as diamond, but it is denser than water. And water is comparatively, compared to diamond and glass, water is an optically rare medium. So when you are doing any problem, or when a light ray is entering from, for example, water to glass, then here water has absolute refractive index to be 1.33 and glass has absolute refractive index of 1.52. That means glass is a denser medium and water is a rare medium. Optically rare medium and optically denser medium. So we can find out which medium is denser and which medium is rarer by looking at its absolute refractive index. Higher the refractive index of a medium is, more the light ray will bend at the surface separating that medium and air. Refractive index of a medium depends on the speed with which the light travels through that medium. For example, here refractive index can be written as speed of light in vacuum divided by speed of light in medium divided by speed of light in medium. So absolute refractive index can also be found by the formula speed of light in vacuum divided by speed of light in a medium. That is, velocity of light is represented by the symbol c and the velocity of light in a medium is represented by the symbol v. So as we said earlier, higher the refractive index, lesser will be the speed of light traveling through that medium. We already said about refractive index of diamond, glass and water. The refractive index of diamond was 2.42, refractive index of glass with respect to vacuum was 1.52 and refractive index of water was 1.33. That means the velocity of light in diamond, and we are comparing the velocities, velocity of light in glass and velocity of light in water. What we see here is light travels the fastest in among these three through water, and the light travels at the least velocity will be in diamond. So light travels the fastest through water and the least velocity of light will be through diamond among glass, diamond and water. Understood? Okay. Okay, next one is conditions for no refraction. There are two instances in which light traveling from one medium will not bend when it enters into another medium. So conditions for no refraction. The first condition is that if the light ray is falling normally on the surface, then there will not be any refraction. Remember, if the light ray falls normally on the surface, the light ray is falling normally on the surface, it will pass through the second medium undeviated. There will not be any refraction. That is the first condition. And the second condition is a light ray traveling in one medium will pass undeviated if the refractive index of both the mediums are same. The refractive index of both the mediums are same, that is refractive index of one is equal to refractive index of the second medium, then there will not be any deflection or there will not be any bending of light ray. So these are the two conditions for no refraction in the given pair of medium. First one, the light ray is falling normally on the surface separating the medium, and the second one is that the refractive index of the first medium and the second medium are same. Next, we are going to look at the change in speed, direction and wavelength, that is change in wavelength, change in direction and change in speed during refraction of light. So, we should remember that a light ray travelling from one medium to another gets refracted due to the difference in the speed of the light travelling in different mediums. So, we know that speed changes, that is why refraction happens, and due to that change in speed, the direction of the light ray bends also. And what happens to wavelength of the light? For example, when a light ray travelling through a medium meets the surface separating the two medium, and if it bends towards the normal, then we say that this is a rare medium and this is a dense medium. Here what we see is, let the light ray be travelling through air or vacuum which is almost close to each other, and it is travelling through a medium, for example water or glass. So what we see here is, let the speed of light be c and the frequency be f, and when it is travelling through vacuum, let its wavelength be lambda. Now when it enters into a medium, its velocity changes to v, or it gets decreased to v, and what we have to remember is, frequency remains the same and its wavelength will get reduced to lambda dash. This is not dash here, that is part of the normal. So what we see here is, frequency remains the same but lambda decreases, so that frequency into lambda, the value of velocity will be less than the value of velocity of light through vacuum. So light ray is travelling through vacuum, it is entering into a medium, its speed decreases, and its speed decreases due to change in its wavelength. So we have to remember, during refraction of light, when light ray enters from a rare medium to dense medium, its wavelength decreases, If the light ray is entering from a denser medium into a rarer medium, what happens is that the light ray will bend away from the normal. Actually it should have gone like this, but light ray is bending away from the normal. In that case, for example, let this be glass and let this be vacuum, and the light ray is travelling from glass to vacuum, and what happens here is, its velocity increases and also its wavelength increases. So light travelling from rare medium to dense medium, its wavelength decreases and velocity decreases. When light ray is entering from a denser medium to rarer medium, its velocity increases, the light ray's velocity increases and its wavelength also increases. Now let us see the factors affecting the refractive index of a medium. Okay, factors affecting refractive index of a medium. The refractive index of a given medium depends on three main factors. The first one is material of the medium. The refractive index depends on the material of the medium. If the light ray is travelling from air to glass, we will have the refractive index of 1.52. If instead of glass we are using water, then the value will be 1.33. If the material is changed to diamond, then the refractive index will be 2.42. So refractive index depends on the material. Next, number 2, refractive index depends on physical conditions like temperature and density. So refractive index depends on physical conditions like temperature and density. Sometimes when temperature increases, density can decrease. This is not optical density, it is the other density, the mass volume density. If density changes, the refractive index can also change. Physical conditions. Number 3 is wavelength of the light. So refractive index of the given pair of medium is affected by the wavelength of the light used. So it has been experimentally found that longer the wavelength or larger value of wavelength will have lesser refractive index. If the wavelength is small, the refractive index will be high. For example, in the visible spectrum, the violet light has small wavelength and red light has larger wavelength. That means violet light will have a higher refractive index than red light. If we are, let there be a violet light ray and a red light ray traveling through vacuum, it is entering into a denser medium, the violet will bend more towards the normal than the red light ray. The violet light ray will be bending more than the red light ray. So refractive index also depends on the wavelength of light. For doing most of the experiments, we use yellow colored light ray, and not any yellow, it is an yellow color produced by sodium vapor lamp, which has a specific wavelength of 589 nanometer. So we use a specific color of light for doing experiments, most of the experiments in refraction of light. Okay, now we have to learn about the principle of reversibility of light. Principle of reversibility of light. This happens in the case of reflection and also refraction. According to principle of reversibility of light ray, if the direction of the light ray during reflection or refraction is reversed, then the light ray will retrace its original path. That means, for example, if a light ray is traveling from a medium into a denser medium, and we know that it will bend towards the normal. This is what we have been studying under refraction of light. So if we place a mirror perpendicularly to the coming light ray, let this be a mirror, and if we place it here, the light ray will retrace its original path and go back in the same direction in which, or it will retrace its original path. It will go to the same direction taking the same path, and this is called a reversibility of light ray. And why this principle is very important. So look at this now. This is the angle of incidence and this is the angle of refraction, and refractive index of medium 2, let this be medium 1 and let this be medium 2. Refractive index of medium 2 with respect to 1, we will get a value, we will get the refractive index of medium 2 with respect to 1. Now the same thing can be applied because the light ray can retrace its original path. If this is the incident ray, the light ray will bend away from the normal and this will be its refracted ray. Then our refractive index here will become sin r by sin I. That is, here first case it will be sin I by sin r, and in the second case, if the light ray is travelling from the denser medium to rarer medium, then we can call it as the refractive index of the rarer medium with respect to the denser medium, which is equal to sin. Here the angle of incidence is represented by r because light ray is going from the denser medium. So here the angle of incidence is r divided by the light ray is bending away from the normal, and here the refracted ray is, this is the refracted ray, the reverse path of the light ray, then it is called a sin I. So when you multiply them both, which is refractive index of the first medium with refractive index of the second medium into refractive index of the first medium, that is equal to sin I by sin r into sin r by sin I, then everything will get cancelled and the value you get will be 1. And why is it important? Because the next step, look, refractive index of a medium is equal to, this multiplication will go under this 1 as division. It will be 1 by refractive index of the first medium. So when light ray is travelling from one medium to another medium, then the refractive index of the second medium with respect to first medium is equal to reciprocal of refractive index of the first medium with respect to the second medium. We have already said that the refractive index of water is 1.33. This is refractive index of water with respect to air, which we write as 1.33. If the light ray is travelling from water to air, then we can calculate the refractive index of air with respect to water, which is simply the reciprocal of which is 1 divided by 1.33, which is equal to 0.75. This is the refractive index of air, refractive index of air with respect to water. So that is how the principle of reversibility of light is important for us, because principle of reversibility of light helps us to find the refractive index of the mediums in both directions. If you know the refractive index of one medium with respect to another medium, then you can find the refractive index of the first medium with respect to the second medium. Okay students, the last topic for today's discussion is refraction of light through a rectangular glass slab. Refraction of light through a rectangular glass slab. Let's consider GHIJ given here. Let it be a rectangular glass slab. Glass slab may be a thick cuboid of a glass, and here GH and IJ are parallel surface. Let a light ray starting from point A falls on the surface GH, and it's the incident light ray, and it falls at the point O, and at point O we can draw a normal. We can draw a normal N dash, and this is air, and this is glass, and again this is air. So light ray here is travelling from air into glass, so it will bend towards the normal. So before drawing the refracted light ray, I will draw the path the light ray would have taken if there was no glass block. The incident light ray would have gone directly like this if there was no glass block in its path. But here at this point it will be deflected towards the normal and reaches the next surface here. So let this be point B. What happens to the light ray at point B? Remember, now the light ray is traveling from denser medium glass to a rarer medium air. So the light ray should bend away from the normal. So first we will draw the normal. Let the name of this normal be M dash, and the light ray will be, instead of going straight like this, it will bend away from the normal. And it will go towards the point C. So don't forget to draw the arrow marks the light ray is taking in the direction on which the light ray is taking. And now what we can see here, the first here we can mark the angle of incidence or the first angle of incidence I1. And here we can mark the angle between the refracted ray and the normal here as R1, because it is the first refraction, because there are two refractions happening. And here we can mark the angle between this ray OB and this normal MB as incident ray 2. This is I2, the second incident ray, because it is the incident ray for this given pair of medium. Then here we can write refracted ray 2. Okay. Now we are going to write the values based on the Snell's law. So from the Snell's law we studied that refractive index of glass with respect to air is sin I1 by sin R1. Sin I1 by sin R1. Then similarly at this junction we can write refractive index of air, because light ray is traveling from glass to air. So refractive index of air with respect to glass is equal to sin I2 divided by sin R2. Okay, we learned from reversibility of light ray, we learned a similar equation which happens to have refractive index of glass and glass with respect to air and refractive index of air with respect to glass. There we studied that refractive index of glass with respect to air, when it is multiplied by refractive index of the same mediums in different direction, that is refractive index of air with respect to glass, when you multiply their values we get the answer 1. So now what we are going to do is we are going to multiply equation number 1 and equation number 2. So what happens is refractive index of glass into refractive index of air is equal to sin I1 divided by sin R1 to sin I2 divided by sin R2. And by the principle of reversibility of light, its value should be 1. And another interesting thing that we can see here is that GH and IJ are parallel to each other. Therefore, the perpendiculars drawn for them, that is N dash and M dash, should also be parallel to each other. If these two normals are parallel, then this is a transverse, this light ray is a transverse, and these angles are alternate angles, and I2 and R1, these angles are alternate interior angles and they are equal. So what I said, angle I2 is equal to angle I2 is equal to R1. Why? Because N dash and M dash are parallel to each other, and OB is a transverse drawn across them, therefore I2 and R1 are alternate interior angles and they are equal. If they are equal, then the sine I2 and sine R1 are having the same values and they can be cancelled. So what is remaining is sine I1 divided by sine R2, which I will write here. Okay, I am carrying it over from here. Sine I1 divided by sine R2 is equal to 1. That means sine I1 is equal to sine R2. This R2 can be carried over here. Sine I1 is equal to R2, that is equal to angle I1 is equal to angle R2. Look at here, angle I1 is equal to angle R2. We have just proved that I1 is equal to R2. And why this proof is important? This proof is important to prove that in a rectangular glass slab, the incident ray and its path is parallel to the emergent ray. Why is it important? We have proved sine angle of incidence is equal to angle of emergence, and it is important because the path of the incident ray is parallel to the emergent ray, and the perpendicular distance between the emergent ray and the path of the incident ray is known as lateral displacement. That is known as lateral displacement. So what is lateral displacement? The perpendicular distance between the emergent ray and the original path of the incident ray is known as lateral displacement. And this lateral displacement depends on four main factors. Lateral displacement is directly proportional to thickness of the glass. It directly depends on the thickness of the glass. More the thickness of the glass, higher will be the lateral displacement. Second, angle of incidence. When you increase the angle of incidence, lateral displacement also increases. Third one, lateral displacement is directly proportional to the refractive index of the given pair of medium. Higher the refractive index, larger will be the value of lateral displacement. And finally, lateral displacement is inversely proportional to wavelength of the light used. If you use a light ray with higher wavelength, lateral displacement will be less. If you use a light ray of less wavelength, then the lateral displacement will be less. That means for red light, the lateral displacement will be less, and for a violet light, lateral displacement will be more. I hope you understood the points which we covered today. We studied about refractive index, absolute refractive index. We studied the values of refractive index of some mediums. We studied about principle of reversibility of light ray. Then we learned about the refraction of light through a rectangular glass slab, and finally we studied about lateral displacement. Please go through your textbook and confirm the ideas that we learned in the class today, and also do the exercise, the ICSE questions given at the back of this session in your textbook, and send it to me through your classroom. Thank you all. We will meet in the next class.